Hello, everyone. The study I'm presenting here is the work of my student, Raj Dave, as his master's thesis. And the study is focused on quantifying shear stresses in a bioreactor heart valve. So some motivation for why we care about valves in bioreactors. If you have a diseased valve that needs to be replaced, currently you have two options. One, you can go with a mechanical valve, which is thrombogenic. And this means that you would need to be on lifelong anticoagulation management. Or you could choose a pig valve, which is a foreign tissue in your body. And so the valve is going to be subject to degradation and also doesn't grow with the patient, which poses some problems with pediatric patients. So this is where tissue engineered heart valves come in. We can take cells from the patient themselves and be able to grow a valve out of those cells. So then you can have a living valve that has the ability to repair and also to grow with the patient. Now, in order to be able to grow those valves, you need to operate a bioreactor to provide the appropriate stimuli to the cells to encourage them to differentiate into the correct cell type. And one of the challenges in the field is that when you operate a bioreactor with a tissue valve in there, you don't really know what kind of shear stresses that you are imparting on these cells on the tissue valve. And so that's the motivation for our study. The goal of the study is to provide a set of data that can help estimate the magnitude of shear stress in bioreactor valves under different bioreactor operating conditions. So the general approach of our study is that we first run fluid structure interaction simulations to simulate the motion of the valve across a cardiac cycle. And we extract the geometry of the valve at different opening levels so that we can use these geometries to then run a fluid dynamic simulation, which allows us to do things like boundary layer meshing and be able to get much higher fidelity flow velocity data with which we could compute shear stress accurately. So we did this for 3 different sizes of valves representing different types of patients. And the fluid structure interaction simulation uses LS-DYNA with a method that was previously published by our collaborator. And with the fluid structure interaction simulation, we extract the geometry of the valve at different opening levels characterized by the GOA, or the geometric orifice area. And so that would be the cross-sectional area of these opening here. With these extracted geometry, we then compute or run CFD simulations to try to extract the shear stress information. So the CFD simulations, these are the simulation parameters. We take the valve geometries, we put them into a fluid domain conduit, and we ran the CFD simulations. For each valve size, we have 5 different geometries of the different opening levels, GOAs. And for each geometry, we ran simulations for different flow rates. And so each check mark here represents one CFD simulation. And so all the check marks here represent all the simulations that we ran. So let's look at some results of the shear stress analysis. So the general pattern of shear stress that we observed looks something like this, where you see peak shear stresses typically at the tip of the leaflet. And then at the base of the leaflet, we have a region with also elevated shear stress. And at the center, we have low shear stress. And we see the same kind of pattern for different flow rates and different valve sizes in geometries. And so here's one example of the same geometry at different flow rates. You see very similar pattern. So with this data, if you're running a bioreactor, you can know that the cells on your leaflet, around the edges, are experiencing higher shear stresses and lower shear stress at the center. Another thing that we did was quantify the distribution of the shear stress across the leaflet. And so what you're seeing here, each plot is a histogram with the x-axis being the shear stress in Pascal. And each row is a flow rate, and each column is a different level of opening or different GOAs. And so all of this data represents just one valve size, and we have 3 sets of these data for each valve size. And a trend that we see is that for low flow, so here's low flow, pretty much the entire leaflet, all the regions of the leaflet experiences pretty uniform level of shear stress, and that's represented by these peaks in the histogram. Basically, all of the shear stress is around some narrow band of values. But at the higher flow, you start to see very different distribution of shear stresses. So you could have areas of your valves that are seeing pretty high shear stresses, and some areas have pretty low shear stresses. And you can see the same pattern if you look at the 3D pattern here. So for low flow, pretty uniform. High flow, you have very different shear stress levels at different places. And so again, with this data, if you're running a bioreactor, you can look at your operating condition of the bioreactor and what your valve is doing and be able to have some idea of what proportion of cells are experiencing what level of shear stress. Okay, another thing that we did was that we were able to construct regression models to summarize the shear stress. And so we actually were able to find a pretty good log-log relationship between shear stress and a function of Q, the flow rate, and the GOA. These regression relationships actually hold true pretty well for different valve sizes, represented here by different colors. So we did this for the 50th percentile shear stress and the 99th percentile shear stress, and this data could potentially be useful. Here's a quick example showing how someone might use this information. So let's say I'm running a bioreactor for a 22 millimeter valve, and I ramp up my bioreactor flow across 5 days. And so these are the flow settings I have on my bioreactor. And when I run these settings, this is the GOA that I observe in my tissue. So with this information, I could use the regression equations to estimate what kind of shear stresses my valves might be seeing. And these regressions seem to be true for different valve sizes, at least within the range that we tested. So I could get data such as this, and this could tell me, for example, on day 3, half of my cell experience peak shear stresses less than 5 Pascal, and half of my cell experience peak shear stresses that are between 5 and 22 Pascal. So that's an example of how I could use this information to have some understanding of what's going on in my bioreactor valve leaflets. So to summarize, in this study, we generate a set of data for tissue engineers to estimate the shear stress in bioreactor valves. And this information hopefully can help tune bioreactor settings and be able to optimize cell maturation protocols. With that, I'd like to thank collaborators and funding sources, and thank you for your time and your attention.